So we've seen recursive functions, and we've used this concept of a list with the functions first, rest, and cons. And I mentioned that we were working with a recursive data structure or recursive data type, but I didn't actually show you what that meant underneath the hood. What does it mean for us to have a recursive data type? Before we get there, I want to talk a little bit about an important concept that is pervasive throughout computer science, and this is this idea of a barrier of abstraction. So notice visually we can think of this as really something that separates two parts of our code. We've got these three functions, and notice that how those functions were actually implemented, the implementation details of Node, we knew nothing about. I told you how these three functions worked relative to one another. When you conned something onto an empty list, if you asked what you got back for first, you would get the thing that you conned back out of it. If you asked the rest, you'd get the remainder of the list, right? So we know what these three functions do, but we don't know how they do them. And that's okay. That's kind of the point of an abstraction barrier. It allows us to hide complexity and think in terms of some bigger picture concept. And so the bigger picture concept that we're thinking in terms of, the higher order concept, is that we can think about this conceptually as a list, and the things that we can do are these operations on the list. And this is an important concept that extends beyond just computer science and software engineering. If you are in business or you have an organization, the way that you think about organizing certain units and how they interface with one another is really important for managing the complexity as organizations grow and need to scale. And so the key idea is Node doesn't really need to know anything about how the other side of this barrier is using it, as long as it's upholding the things that it advertises it can do. It's successfully fulfilling the requirements of cons, first, and rest. And on this side of the abstraction barrier, the code that we write just needs to know that those things are going to work. It doesn't necessarily care how they were implemented. But in this next video, we're going to look at how, in our case, were these three functions implemented. Okay. So what this allows us to do is simplify our code and not create unnecessary dependencies on many details. Right? So we can implement these things differently, and you would be free to change your code as long as you knew that you were using these three functions. And if we wanted to change how these three functions were implemented, we would be fine to, as long as they still behaved the same way. So as long as there's no perceivable difference in how these three functions behave, these sides become independent of one another and can improve on their own. And so this is what we think of as an abstraction barrier. We've created an abstraction, the idea of a list. All right, well, let's go look at how we actually implemented that. And first, I want to bring us back to this idea of a compound data type. So remember when we talked about classes, the unit we just came out of, classes are bundles of effectively variables that are, we call them properties in the context of a class. So this person class has a name property and a pets property. And notice that we could make a pets property where a person has many dogs, right? Just like we saw in the simulation example, a model had many cells in an array and its population property. Here we've got a person who has many pets that is an array of dogs, and dog is another compound data type made up of two string values or two string properties, name and breed, right? So what's new about what we're looking at today is this idea that we can have a recursive data type. So class node can have a next property, which is going to refer to the next node, just like we saw in this linked list, right? We had a node that had one value in it, and that value will be stored in the data property. So let's imagine this is a node that stores string values. And the next node would be another node value that it refers to. Right? So this idea that a property can have the same type as the class it's defined in is what makes this a recursive data type. Right? And so this allows us to reference the next node, the next node, the next node. And so if we were to think about this visually in our environment diagram, we would have a node object where the next property is a reference to some other node object. And this continues on recursively until we reach the end of our list. This allows us to form what we call data structures. And data structures, we can imagine coming up with more complex data structures than what we'll call a singly linked list, because a singly linked list is perhaps the simplest data structure you can imagine. And each of these data structures has different properties and uses, right? So we're looking at a linked list, and we're using cons, first, and rest to manipulate a linked list. In 410 or 210, actually, if you're continuing on to 210 in the fall, what you'll see is that you can have trees, right? And so a tree might have two elements that are two different properties in a single object. The left element would be the left side of the tree, and the right element would be the right side of the tree. So rather than being a list, which is linear, you could imagine having a data structure where one element can have a left side, which is also going to have a left side and a right side until they reach the null values or the ends, and a right side. And this would form like a tree-looking data structure. So the linked list is one of the simplest and most classical data structures that you'll see in computer science. And as we've learned, it's formed by chaining together a sequence of objects, right? Typically, when we're thinking in terms of actually at the node level and we're thinking about the objects, we would tend to call whatever variable it is that we refer to the first node object in our linked list as the head node. So the head node tends to be the very first one in our list. And then what follows is the rest of the list. And so linked lists, as we've seen, actually are a little bit more cumbersome to work with than arrays. However, they're a really good, simple data structure for beginning to better understand null values. So we're seeing null for the first time explicitly here. And null values are useful when we want to make a reference to nothing, right? So we're seeing this for the first time, this idea that we can have a variable that's an object. So next should store a reference to another node, but notice that we're assigning a null reference to node, meaning it refers to nothing. There's nothing that it's going to refer to next. This is the end of our list. And so a linked list gives us the ability to represent null and think about null in a meaningful way. And we're getting more practice with references. So each of these references, because we're storing references to an object type, these would be arrows in our environment diagram. And then the linked list works really, really well when paired with recursive algorithms, which is our focus in this unit. So what is the recursive properties base case? Well, I've already alluded to this, right? It turns out we can assign null anywhere we're assigning a value to, or a default value to a reference type where we expect either a node object or a null value, meaning there's just no node value here. Right? And so this is what resolves the infinite recursion problem of a recursive data type, right? So here we say we've reached the end of a linked list when the next value is null. And so by default, if we were to make a new node, it would be the last node in the list before null is reached. And you can imagine we can form chains of nodes or a linked list by saying node.next is going to be some other node reference, right? And so this is what allows us to signify or signal the end of a linked list in a recursive data structure. This is why we would say our lists are null terminated, meaning we know that we've reached the end of a list when we've reached a null value as the next value, right? So how were cons, first, and rest actually implemented? Well, it turns out in a really naive and simple way, right? So we're putting wrappers around some of the object-oriented concepts we saw in the last unit. So cons, you give it a string in the next node, and all it's doing is constructing a new node value, assigning each of those properties we just saw, and then returning that value right back to you, right? Or the reference of the new object that we created. First is just accessing the data property of that node value that you passed to first, and rest is giving you the reference of what comes next, right? And so these are very, very simple little functions. And the reason we're choosing to use these functions rather than thinking about them from an object-oriented sense is we move out of our unit on object-oriented programming where we're really focused on methods and constructors. We're moving out of that and towards the functional programming model where we're going to be thinking much more in terms of functions. And what we'll see is as we get more practice writing recursive algorithms, especially list processing algorithms, is that this thinking in terms of functions and recursion really pair beautifully together, and we'll get to experience the great joys and beauty of recursion in the weeks ahead.